I'm going to see that tonight.
So let's start off with a couple of hopefully relatively simple questions, one where you're dropping the magnet. So this hinges off of one idea, and if your initial thought process is wrong, everything is going to go wrong, okay? You have the North Pole of the magnet up here. You don't know which direction the field lines are coming from that magnet, you cannot answer this question, okay? So, which direction are the field lines moving from the magnet itself? North to south, south to north. North to south. So this is coming, starting here, and coming around here like this, okay? Because if this starts wrong, everything's going to be a train wreck, okay? So, from the plane of the wire, okay, here's the magnet. So, in the plane of the wire, are the field lines coming up through the bottom or going down through the top?
Up to the bottom.
Coming up through. So, if you're the loop, see the loop, be the loop. If you're the loop, what are you seeing? Dots or X's? You're seeing dots. Are the dots getting more intense, or are you seeing fewer number of dots? More dots, because it's falling towards it, right? Okay, you're getting closer, the magnet's getting closer to the center. Okay, it's getting closer to that. So, you're increasing the number of dots. So what's Mother Nature going to do? So Mother Nature is going to make X's within the plane of the wire. So which direction is the current that's going to make more X's within the plane of the wire? Clockwise or counterclockwise? And no, we're not asking Scooter this question.
Clockwise.
Clockwise, okay? Because of the fact that if I put my hand like this, I curl my fingers on the inside, so initially it's going to be clockwise. Now, the next part of it says, as the magnet falls towards it, then falls past. Now, when it's right in the middle, okay, at some point the current has to like switch signs, okay, it's AC current. So you're going to go from clockwise, and then as it falls through, then what are you going to experience?
Decrease in X.
Yeah, so then you're going to sense a decrease once it falls all the way through. Then you've got the north end, and so that's going this way. So you're decreasing X's. So what's Mother Nature going to do?
Make more.
There you go. So, anyway. All right, so let's talk about that question with the loop. If you get done with that question with the loop wire on the bottom, if you get done with the test and you have not answered a question like this, you have done something horribly wrong. So, what do you got?
A loop of wire.
That second question on the bottom.
A magnet.
Basically, the question you just did in the lab.
And?
Are you asking what our answer is?
Yeah.
Oh, B.
B.
B, absolutely. Okay? Counterclockwise current?
Didn't you not just like read it?
Okay, all right. Shh.
Whoa.
No, that was on me.
I know.
It happens.
Yeah. You said extra credit?
We're on to the second question, Charles.
We don't really have to do anything.
What is a velocity selector?
There's no method of it.
Oh, that's you pick the velocity of an object. It's a object.
Sounds like a cheat code.
I didn't do all those. That sounds terrible.
What? What is this? Don't smile at me like that.
Oh,
What is
no.
this? Don't give me that
Please
condescending.
don't say that.
No, that was a spy of Edmund Doom.
I need to go play the thermostat.
We're literally.
I need you to be like my baby. You're like, Kevin.
He's gotta play the ominous music for his days.
Okay, so the first question, the answer is A. On the second question, the answer is B. Now, go to the question that has like this one, the 2011 number 5. I promise you, there's going to be a version of this question on the test. It's one where it has the radioactive source and the positive charge flowing through it. So, before you even try and sample the problem, just stop, okay? Just stop. Listen, let me paint the big picture. Because this is one of the most important experiments that happen in like how we figured out the mass of subatomic particles. So, you have a radioactive source. All you know is that it's going to be shooting out some positive charge, okay? If this was Ernest Rutherford, he was shooting out an alpha particle. It actually had a charge of 2+. But it's a positively charged particle. So, if you look at what it's going through, there's two regions. You've got a negatively charged electric field at the top. You have a positively charged field at the bottom. Now, let's just do not worry about magnetism. Just look at the electric field. So when that positively charged particle goes into that electric field, which direction is it going to be deflected? Up or down? Up, because it's going to be attracted towards the negative and repulsed by the positive. So the electric field itself is going to want to push this thing up towards the top, right? And if there's no magnetic field, that's what's going to happen. Now, how could you find the strength of the force acting on the charged particle strictly from the electric field? Feck, right? So the force would be Eck. If you knew the strength of the electric field and you knew the charge, you could find the force that's going to drive that up. If you read the question, it says, hey, well, that's great, but we want this particle to go straight, but we know it's positively charged, because that way you can get it going in a particular direction. So this is going this way. Now, let's talk about this. What's the only thing that affects the value of that force? What are the only two things? The value of the electric field and the charge. Does the mass of the particle make any difference at all? No, not part of the story. Okay? The mass at this point is not part of the story. Could be a proton, it could be a lithium ion that has its positively charged or lost an electron, could be iron. Doesn't make any difference. As long as it has a positive charge, it's still going to experience the same amount of force. Now, but we want it to go in a straight line. So now we're going to introduce a magnetic field. Okay? So, just start with this idea. If you wanted to go in a straight line, which direction does the force have to act to make it go in a straight line? It must act downward. Now, what's going to be the value of that magnetic force relative to the force from the electric field? They have to be the same, okay? Because these forces have to balance each other out. So, how could you find the value of the force created by the electric field? What's an option? Excuse me, the force from the magnetic field.
Bill.
I could use Bill. Okay? That's an option. Seem reasonable? Why not? I don't know the length and I don't know what current. Okay? Probably not. What else you got?
QV.
QV. Just QV?
QV.
QVB. does that have some wheels? Yeah? Because if you know what the charge is, it's positively charged 1.6 times 10 to the negative 19. Measuring, you can measure the velocity and you can measure the magnetic field. So, here's the point, is that if you set the electric field equal to the force from the magnetic field, and that's EQ, and that's going to be QVB, what's going to happen to the charge? It's going to cancel out. Okay? All right? So the E is going to cancel, the Q is going to cancel out. So what you're left with is E equals VB. Now, let's talk about the direction of the magnetic field. You have four options. The direction of the magnetic field could point up, could point down, it could point into the page, it could point out of the page. Connor S., what do you got?
Out.
Why?
Right hand rule.
I don't know what to tell you.
But let's expand on the right-hand rule a little bit.
Because force down and velocity that way.
So you got a positively charged going this way, right? Your thumb is pointing in this direction. You want the force to act,
Down.
so that your index finger is pointing
Out.
out of the page. Okay? So I know that the magnetic field, and this is why, if you look at that diagram, why you have dots. Okay? This is why there are dots. Now, what if it had been an electron? Would you still have would everything stay the same?
No, because left hand rule.
Hold on. Hold on.
It made it act the other way.
Hold on. Stop the bus. Stop the bus. Would this equation change?
No.
You can still set the strength equal to, the two forces equal to each other. Okay? True with that.
What the direction?
Which direction would the electron move in the electric field?
Opposite.
The electric field is going to want to be pulled downward. Okay? But now you got to use the left-hand rule, right? So to speak. So if it's an electron, it's coming in, right? You want the force to act which way? You want the force to act upward. So which direction does your finger point? Still points outward.
That doesn't change.
Doesn't matter. Okay? Doesn't matter. Because of the fact that it still has to balance that out. Now, with that said, what?
Do that again.
Electron's going this way. Would you agree that the electron is going to get pulled downward by the electric field? So if you use the left-hand rule, okay, to balance out the pull from the electric field, the force would have to act upward, right? So if I do this, I want the force to act up.
What are your fingers doing?
What are your fingers doing,
Should
Charles?
not be. Yeah, there you go.
Okay? So which direction do these fingers point?
This needs to be up.
Yo. Dude.
You got it?
Hey, tuck in the rest of your fingers. Just,
Charles, you not know how to right hand rule?
Okay, Monday's gonna be long. Okay? Cue the intending doom music. Wah, wah, wah. Okay, now,
it's not about one.
it's really not that
What are
difficult.
your fingers doing?
This way.
This way is not a response to that question.
What are you doing?
Okay.
This way.
So, with all of that said, let me explain what I would look for on a question like this. So on part one, it says derive the equation. They even tell you, hey, this is what you need to get, that you need to get that V equals E over B. So this one was kind of cool, because they basically said, here's the equation that you need, prove how you get there. Okay? But it's the same idea. Oh, we prove that the electric field is equal to the magnetic field. You use QVE, you use FEC, you set the charges cancel out, and you end up at that point. Okay? So basically said, here's where you need to be, get there. So then, on part two, it says some particles emitted from the source has speeds greater than EB1. So, give part two on A some thought. What?
I thought you were gonna like nod your head at me with the like screw. Yeah, I got it.
What do you do? What are you pointing?
For no shoe.
What are you pointing? Upward?
Okay, I have another answer.
That was fast. What are you going for?
That's gonna work. That's
Ah.
It doesn't change the distance.
Wait. Like,
The distance is the
Is this all they want for the
because
first
QED
one?
is greater than
same.
EQ.
Yeah, that's what I was thinking.
I was gonna say the same thing, but then I was thought it was
Yeah, on the right.
The electric field is the one that's pushing it. Like this.
Or B would be smaller.
Well, but you gotta like more velocity pushed.
No, it's
But we're not trying to equalize it.
Field.
Exactly.
The initial magnetic force.
Oh, and region
I disagree. I guess we'll just see on that. Yeah. The curve toward the bottom is good. That's what I said. Yeah, they're right.
Those are that's going in distance.
Yeah, I'm right.
Because it's a pocket. Like, you're the same person.
Okay. Danny, are we recording by the way?
Yes.
Okay. All right. So, I just forgot all about that. So what do you have for part two? Thatch, you had a good explanation.
I said it curves toward the bottom of the page.
Why?
Because if you set your two forces equal to each other, and then you like put the equations in, you have QVB equals EQ, and velocity is only a factor in one side of the equation, and if you're increasing that, then that means your force, magnetic field is greater than the force of the electric field.
Fantastic. Couldn't give a better explanation. Okay? So here's what you got. You have to look at what is a factor and what is not a factor. Is mass a factor at this point?
No.
No.
Must never will.
Charges, they're gonna cancel out. But if you look at where it's exactly what Thatch said, velocity impacts the strength of the magnetic force. So as the velocity gets bigger, what's gonna happen to the magnetic force side?
It's gonna get bigger.
It's going to get bigger. Then you have to go back to the right-hand rule and go, okay, hey, I got a positively charged particle coming in, the magnetic field is coming out, the force is gonna be pointing downward, so that's going to get bigger, so the particles will drop down. So the beauty of this is, and from a scientific experiment, what they do is at the end of this, they have an opening, right, like this. And so what will happen then is that you're only allowing particles with an exact velocity to make it through. Now, if they're going too slow, what would happen?
That would just get sent up to.
Yeah, it would just be the opposite. So if they're going too slow or they're going too fast, and again, I don't want you to get the idea that these are like little cars that we can see going across the screen. This is typically like the nucleus of an atom or just a single proton. You can't see these. So what they would do in the old days is that they would have a phosphorescent screen. And when these particles would impact this phosphorescent screen, it would be in a darkened room. And you would see a flash of light. So that was the detector. You couldn't actually see these like, oh, there goes one. Oh, watch it. Okay, number one, they were probably traveling something close to the speed of light. They were so small that you couldn't see them, so what you had to do was set up ways, okay, how can we detect where they're at? So then you would set up that phosphorescent screen, and then you would only see particles going through there that had a particular speed. So basically it was a sorting process. You would sort out only those particles that you knew had a particular velocity that would make it through there. And if they were positively charged, they would go through there, and then you would know exactly what you had going out. Okay, so with that said, move over to the back side of that question.
Hey, Bert, I have
What?
a request for the test.
Huh?
Can you boldly explain your reasoning?
Can I boldly?
Yeah, can you like just bold explain your reasoning, like bold it so I can see it?
Connor, just
You
open
could
your
read
eyes.
the whole
Expression
question.
for the
Yeah.
charge to mass ratio.
Every time we've had a question like that,
He normally
sorry, I'm
leaves
sorry,
lines.
because I don't see it.
I don't know what you want from me, Conrez.
I don't know what you want from me, Bert.
I want thoroughly
I might not do the most.
thought out, well-worded explanations.
Saying last time on the test, I didn't even see the explain part, so I just didn't.
When in doubt, explain. You've been my student long enough, okay?
No.
When in doubt, write it out.
A couple more years and I would know.
Is the photon a boson?
To be or not to be.
That is the question.
Oh,
That's not me, let's go.
Here.
what? What are you talking about here?
Wouldn't you agree?
Is it going all the way through region one?
Yeah.
It's like, no, don't even.
So it would go up.
Now, I will tell you this, Connor, in terms of what you read, don't just jump straight down to B. It says, express algebraic answers in terms of E, B1, B2, and Q, and fundamental constants as appropriate. So pay attention to what you need in your variables.
Wow, that's crazy, because I he didn't do that.
That's why I just pointed that out to you.
Forces. Yeah. Initial magnetic
I
force.
don't know how to, I don't know how to.
That's so.
Do
we don't have
I'm not as.
Huh?
I don't know.
E has me befuddled.
Yeah.
And
What do you mean?
I'm not sure I called
Charge to mass ratio, what is that?
You got
I didn't know
nothing.
what it was.
It's an impossible question to answer.
Okay, I'm okay with that. Let's not do it.
We should not do it. I like this question. That's fine.
What is centripetal force equal?
Centripetal force. What is
it's saying then
It's
centripetal force.
and something, hold on.
It's
There's no electric
Oh,
fields
yeah,
on
B
the
squared over
second
there.
region.
Why is
No,
there
it's
a
just
B
magnetic.
squared all it was?
what it's saying.
Okay.
When does that come?
So let's talk about B.
Confused.
So let's again, hopefully this is old hat. Start with the idea that you're only in a magnetic field that's now going into the page. So once you clear this, okay? So at this point, you have positively charged particles that are traveling at a known velocity, okay? So you know, hey, these are only coming through with this particular velocity. And now you're going into a magnetic field that's going into the page. So you got a positively charged particle going like this. The magnetic field is going into the page, so what are you gonna do? What's the direction of the force gonna be? Up, right? Now, an interesting thing happens. As it continues even up to this point, once it gets to this point, what's the direction of the force? If you're here, magnetic field is going into the page, the force is going to act. So as it goes around, it's the same inward force going to act on it all the time. Ooh, that might make it move in a. Ooh,
And that's why
Stays
they
in the
use
region.
no.
You're so smart, Mr. Burkamp.
Huh?
You're so smart.
Huh?
You're so smart.
No.
What a revelation.
Made a lot of mistakes.
I think she
So,
got on the test first.
Here's the story.
Then
So let's talk about B. So the force, right, in the second region is still going to be QVB, but that's going to be B2. Okay, not B1, that's going to be the second magnetic field. But it says up there to express it in terms of EB1, B2. So there's a region, or there is a reason, we found that initial velocity to be the ratio of E1 to B1. So guess what we can do down here? Instead of V, we could put what?
What?
What did velocity equal from the first part?
E over B.
That was E1 over,
Wow.
times B2. True? That's why we did that first part.
Oh, that velocity.
Okay, all I did was a substitution, right? So I could write this as QE, and then the ratio of B2 over B1. Now, here's why this is important. From a lab perspective, it would be virtually impossible to measure the speed of a single proton or alpha particle going across this gap. Okay, you could not do it. You can't see it. You don't have a stopwatch. It's approaching the speed of light. You can't go boom, boom, got it. Okay, no. But what you can measure is the strength of the electric field. Oh, okay, we can do that. You can measure the strength of your magnetic field. So physically, those are much easier to measure than the speed of a proton that you can't see that's going across this gap. Okay? That's why you set it up like that. Now, when you get to C, it says, describe the changes, if any, in the magnitude and direction of the magnetic force as the particle moves into region 2. So as it goes around into that region, is the magnitude of the force going to change? No. But is the direction going to change?
The direction of the net force changes.
Yes, but it's always going to act inward, which is going to make it move in a
Circle.
circle. Ooh. Okay? Cool. Now, then when you get D, it says describe the path of the particle in region 2. Guess what?
Circle.
Circle. Half circle in this point. Now, here's the whole point of this problem, is E. Drive an expression for the charge to mass ratio of the particle, specifically note any quantities not previously defined that are included in your answer. So here's where this goes. And Gapshawn is going, we've got no mass. But it's going to move in a circle. Do particles want to move in a circle? No, what do they want to move in? Oh! So,
the radius of your circle.
hold on, just we'll get there. So the magnetic field is creating what? The centripetal force. Oh, right. Okay? See where we're going with this? Now, the magnetic force, right? The magnetic force is going to be, or the centripetal force is going to be mv r squared, right? Simple thing. We've done this 100 times. Centrifugal force is mv squared over r.
Yeah, MV squared
That's
over
what
R.
we're-
Oh, mv squared over r. My bad. Okay? I got a little, I put squared in the wrong place. You're like, whoa, when did this change? Okay, mv squared over r. Now, how can you express the magnetic field force? You could do QVB. But, which B are you gonna use? B2. But we don't want velocity. So we could use the same thing and go E over, just as we had up there, right? We can put that as E over B1 times B2. So, you got mv squared over r. So, if you go through the math, and they want specifically a charge to mass ratio. So, if you do this, you got Q over M, and then you just move everything else to the other side. So, here's historically how this played out. Is that you can measure electric fields and you can measure magnetic fields. Now, how you got the radius was kind of cool. So what they would do is they would send this through. And then up here, they would have like another phosphorescent screen. And what they would do is they would measure where you saw those flashes of light occur. So then, from that, you could measure the radius of that arc. Okay, cool. So then what would happen is that you would know everything on the right side, and then you could have that charge to mass ratio. So, once they figured out the charge on the electron, or the proton 1.6 times 10 to the negative 19th, then they could figure out the mass of the particles. Because there's no way to take a proton and take that and put it on a scale and go, oh, there's the mass of the proton, 10 to the negative 31st kilograms. Got it. Cool. Okay? No. But now, here's an interesting thing happens. If you look at this, and if these things are equal, so you're always going to have the same, as long as they're positively charged. This is where you think through the ramifications. As long as they're positively charged, whether it's a proton or an iron atom that you've taken away an electron, if it's singly charged, the mass is not going to affect the QVB2 part of that. Mass isn't part of that equation. But over here, as the mass is going to get bigger, because the velocity is going to be the same, as the mass gets bigger, what happens to the radius? It also gets bigger. So if you can measure the radius of the arc, then you can figure out, oh, what has to be the mass of that particular particle, because the radius changes as the mass changes. Like that, Sydney?
Yeah, it all came together.
Good. Now, why are neutrons so difficult to measure?
They don't have a charge.
Yeah, you send a neutron through, what's going to happen?
Nothing.
Straight.
Absolutely nothing. It's just going to keep going straight. Okay? I promise you, if you hand in the test and you haven't done something like this on the test, you have done something wrong. Okay? It's going to be the last problem on the test. Okay? So, it isn't like I'm going to give you the test and go, oh no, I didn't tell you what was going to be on. I promise you, you're going to have a question like this on the test. Are my track people leaving me?
Yes.
Okay, fine. Okay.
We'll spin.
Try the 2009 number 3 with the wire and the resistor, because that combines a whole bunch of different things.
Wait, which one are we trying, bro? Oh.
The one with the wire, question number 3.
I'm too tired to do this.
All right, Danny, stop the camera for a minute.